In this video, I'm going to do a quick recap of thermal expansion and how we solve thermal expansion problems in mechanics of materials, and then do one more worked full example of thermal expansion. So as a reminder from last time, we can calculate thermal strain using a simple equation, alpha times delta T, where alpha is our coefficient of thermal expansion and delta T, delta capital T, is our temperature change. We then take that and use our definition of normal strain to get from that a thermal deflection, lowercase delta t, which is alpha, thermal expansion coefficient, times the temperature change, capital delta T, times the original length of the bar. If we have free expansion, the picture looks like this. I could have a bar that is fixed or pinned on one end, free on the other end, and it experiences a temperature change. We'll say it's an increase in temperature. The bar will want to get longer, and the amount of length change will depend on how big the temperature change is, how long it is, how big the coefficient of thermal expansion is for the material, and this right here we would call our thermal deflection. It's the length change. Quick and easy to calculate for free expansion. We can also have a situation where we are free to expand, but we also have an applied load. So the picture is similar. Fixed on one end, free on the other. We apply a temperature change. Let's say somebody pulls on this with a load P. You'll experience length change from both of these. The thermal length change will be the same exact delta thermal that we calculated before. And then in addition to that, we'll have another superimposed length change, delta mechanical. So in this case, our total deflection will just be the sum of delta thermal plus delta mechanical. And then we can replace those with what they're equal to. Delta thermal, that's alpha times the temperature change times the original length. And then we add to that our delta mechanical, which is our applied load P, our original length L0 over AE. If we wanted to find deflection but just strain, the total strain could also be determined as a sum of the thermal strain and the mechanical strain. And what would those look like? We calculate that as delta total divided by the original length, right? Because normal strain is change in length over original length. That would be your total strain. You could also decompose this and call it alpha delta T. There's your thermal strain. And then your mechanical strain would be P over AE. Now, what if we want to find the stress in this situation? Stress is going to be Young's modulus times only the mechanical strain. Because remember, when we have something that is free to expand, there is no induced stress. And this is free to expand, so the thermal part does not induce any stress. Only P induces stress. And let's just plug in what this is equal to. We get E times P over AE, which is just P over A. That's what we expect. Normal stress should be force over area, and it is. So when it's free to expand and you add a load to it to calculate the stress, you're just going to use the mechanical part of the strain or the mechanical part of the load, and you're done. There's no real coupling between temperature change and stress. They're completely unrelated to each other when you have free expansion. We worked on last time was the confined situation, where we are fixed on one end. We could have a gap, or more simply, I'll just draw it assuming we're fixed on the other end. Now we apply a positive temperature change and it wants to get longer. So without any externally applied load, what's going to happen is it wants to get longer by delta thermal. It's not able to, so you end up with an induced compressive load that pushes it back the other way, a delta mechanical. And what we need is that the magnitude of delta thermal has to equal the magnitude of delta mechanical. With the picture drawn this way, when I write my compatibility condition, I want to write it as delta thermal minus delta mechanical equals 0. And the reason for that is that I am drawing P in compression, treating a positive delta mechanical as getting shorter. So I need to subtract them from each other because of the fact that I drew this P in compression, drew delta mechanical, the direction it's going to act. There is another way to do the signs for this, which you might prefer. The other way to do the signs for this is I would draw the picture still constrained, and I would draw it as delta thermal goes that way, and I would draw my P as being in tension and draw delta mechanical as also going in that way. Then the equation that you would write to go along with that would be delta T plus delta M, because they're both going in the same direction, so we're going to add them up, they have to add up to 0. And you'll end up getting that delta M needs to be negative, meaning you drew P in the wrong direction and delta M is drawn on the picture in the wrong direction. I tend to prefer to draw them in the direction they're actually going to act, which means I need to say that the thermal, however big that is to the right, minus the mechanical, however big that is to the left, they've got to end up being 0 when you subtract them. Let's do a really hard example. This example is a composite bar. This part in the middle is a steel core, and it's got a brass shell around the outside. And I have some properties here. This steel has got a Young's module, so 200 gigapascals. The coefficient of thermal expansion for this steel is given, as are the material properties for the brass. And we're told they are bonded at this surface. What we're then asked to do is to find the largest allowable temperature increase so that the stress in the steel stays below a key value. It may not look statically indeterminate, but it is statically indeterminate. And the way to figure that out is to kind of draw a little picture. And I'm just not going to do this in 3D. There's no need to do this in 3D. We'll just do a side view of it. So I've got my steel core, and on the side of it is the brass shell. Just draw that much of it. Because of the temperature increase, the whole structure wants to get longer. And you notice this is not fixed up here on the top. I'm guessing it's probably sitting on a support of some kind. The whole structure is free to expand, so it is going to get longer. Maybe here's going to be the new length of the structure. The problem is our two materials are mismatched in thermal expansion coefficient. So one of the materials, the brass, wants to get longer than the steel, but they're stuck together so they can't have a different length change. They're going to have the same length change. The new length is going to be right here. It's going to be non-zero, but I don't know what it is. Now what's going to happen is the thermal expansion of the brass is going to be bigger than that. Pretend it wants to get all the way up to there. There's my delta thermal for the brass, whereas my delta thermal for the steel is much shorter. It's right there. Delta thermal for the steel. They're different. So what's going to happen is the two materials are going to pull on each other. The steel is going to hold that brass back and say, you don't get to get that long. You got to come back and meet me in the middle. It's not exactly the middle, but meet me somewhere in between. So right there is going to be our delta mechanical for the brass. But the brass is going to say to the steel, hey, I want you to get longer, so come meet me partway. So the steel is going to move up to delta mechanical for the steel. You're going to have an internal load in the steel that's tensile, right? The brass is pulling up on the steel, while the steel is pulling back in compression on the brass. Let's just working with this right down to compatibility condition. I'll have a total deflection of the steel. And can you see that it's got to equal the total deflection of the brass? Because they're stuck together. It's not going to be 0. It's going to be non-zero, but they have to be equal. So now let's break up the steel and the brass. The steel is going to be a delta thermal for the steel plus, because they're both going in the same direction, delta mechanical for the steel. And then on the right, we're going to have delta thermal for the brass is also getting longer kind of a deflection, but then the mechanical's holding it back. So we're going to have minus delta mechanical for the brass. That's the idea for compatibility. Here's your total deflection for the steel. It gets longer a little bit from thermal, and it gets longer a little bit because of a mechanical force that's pulling out on it. The brass, on the other hand, gets really longer with the thermal and then gets subtracted from it, gets held back by its compressive mechanical loading. Delta thermal for the steel, that's alpha steel, temperature change, times the length of the steel. Delta mechanical for the steel, well, that's the force in the steel, length of the steel over area of the steel, modulus of the steel. And on the right-hand side of the equation, I will have alpha for brass, delta T times the length minus the force in the brass times the length over the area in the brass times the Young's modulus in the brass. So just replacing thermal deflections with alpha delta TLs and mechanical deflections with PL over AEs. Did you notice that the lengths cancel? Now let's do a free body diagram. So I'm going to cut this open, and what I've got is in the middle, we assume it's in tension, it's going to be the force P in the steel. It's getting pulled outward by the brass, which means if you cut it open, that internal load is tensile. And the brass is going to have a load the other direction. I'm going to draw it here as if it's kind of like split up half on each side. I mean, it's really a rectangular shell. So altogether, there is a net compressive load. In this side view, you could draw it as half of it on each side. I think that's the easiest way to draw it. If I sum forces in that direction, I get that the P in the steel has to equal P in the brass, right? They're pushing and pulling each other with an equal and opposite force. So this was my first equation right here. Here is my second equation, because remember with statically indeterminate problems, we're always combining the results of a compatibility equation with the results of an equilibrium equation. So what do? I'm going to take this and get rid of one of the P's. I know the alphas, but I don't know P and I don't know delta T. So I'm going to need another equation to solve all of this in the end. What was I told? I want to keep the steel stress to 55 megapascals. Well, let's write that down as an equation. Equation number 3, we want the stress in the steel, we'll just set it equal to 55 megapascals and know that that would be our maximum temperature. How do you calculate the stress in the steel? Well, that's going to be force in the steel divided by the area of the steel, and that has to be my 55 megapascals. So there's equation number 3 that I should be able to use combined with this, combined with that, to solve for all of it. So let's plug in some numbers. I'm going to start with equation 1 and just plug in everything I know. So first thing I need is coefficient of thermal expansion of steel. That is 11.7 times 10 to the minus 6th per degree C. I need the temperature change, which I don't know, and I already canceled out the length. Plus, okay, wait, this next term, force in the steel over area of the steel, that's the stress in the steel. I know that needs to be 55 megapascals. So let's plug it in. 55, a megapascal is a times 10 to the 6th Newton per square meter. This is the stress in the steel, which is P steel over area steel. And what else is in that part of the equation? I already canceled out the length. I just used P over A, so I just need to divide it by Young's modulus of the steel, which is 200 times 10 to the 9th newtons per square meter. That's the whole left-hand side of the equation. The right-hand side, I need coefficient of thermal expansion for the brass, which was 20.9 times 10 to the minus 6th per degree C, delta T that I don't know, and then I need to subtract from it. I don't know P in the brass, but I do know that P in the brass is equal to P in the steel. Do I know P in the steel? I can find it probably using this equation. P in the steel over area of the steel is 55 times 10 to the 6th newtons per square meter. P in the steel will be 55 times 10 to the 6th newtons per square meter times the area of the steel. I don't remember what the area was. The steel was this little square core, 20 millimeters by 20 millimeters. I think I'm going to switch that to meters. 0.02 meters times 0.02 meters. That's the area. So P in the steel comes out to be 22,000 newtons or 22 kilonewtons. That is also equal to P in the brass. So up here in my equation, I'm going to plug in my P in the brass, which is the 22,000 newtons. Now on the bottom of the equation, I need, what was it? Area in the brass times modulus of brass. Well, that area is a little bit of work to get. The way I ended up doing it was to say, well, I'll just take the area of the outside square, which is 30 by 30, minus the area of the inside square, which is 20 by 20. 0.03 meters squared minus 0.02 meters squared. So this guy is P brass, which is equal to P steel. This guy is the area of the brass, and then the modulus of the brass was 105 times 10 to the 9th newtons per square meter. We just need to simplify that and solve for delta T. I did one additional step, 11.7 times 10 to the minus 6th per degree C times delta T. That next term becomes 275 times 10 to the minus 6th. It's dimensionless because the newtons per square meter cancel on the top and bottom. Just like here, we should have newtons per square meter canceling the newtons per square meter on the bottom. And it should be dimensionless because this is going to have units of degrees C divided by units of degrees C, which is also dimensionless. And the right-hand side of the equation is still 20.9 times 10 to the minus 6th per degree C times delta T. And that other term, we have minus 419 times 10 to the minus 6th. Solving, we get that the temperature change that this bar can handle is 75.4 degrees C. And at that point, the stress in the steel will be right at 55 megapascals. An interesting follow-up to this question might be, how big will the stress in the brass be right then? The stress in the brass is going to be P in the brass divided by A of the brass. That's it for this example. It's a statically indeterminate thermal expansion problem, but it's not a constrained problem by walls or pins. It's constrained by the two materials being attached to each other. When you put two materials together that have dissimilar thermal properties and then you heat them up, they're going to want to change different amounts, and that can cause some really interesting deformations as they kind of tug and pull on each other. And that's what happened here. The whole thing wanted to get longer, but the steel, which had the lower thermal expansion coefficient, did not want to get as long as the brass, which had the bigger thermal expansion coefficient. This picture is really helpful at getting the right answer. Two keys were, I did look at which alpha was bigger. The bigger alpha is the one that's going to start out longer and then end up being compressed as it has to get pulled back to where these guys are going to meet partway. And the one with the lower thermal expansion coefficient is the one that has to get pulled out longer. It is very, very helpful in solving these problems to recognize which one wants to expand more and get this picture right. It also is very helpful if you can get some kind of a free body diagram sketch to help you recognize which one's going to be in tension and which is going to be in compression. Hopefully you found this additional thermal expansion example helpful.